Students, hello. I hope you're all doing well. Let me welcome you to week 10 of the course. Okay, we've reached double digits weeks. So we will continue with reinforcement learning and look at two very central topics today. Uh, First is the notion of what is called multi step returns. So, this is something I had promised you at the end of last week's lecture. So, last week we introduced bootstrapping. So, at one extreme was TD0, okay, which was doing a lot of bootstrapping, and the other extreme was Monte Carlo methods, which were not bootstrapping, they were only relying on empirical returns. And I said there is this family of algorithms for doing some amount of bootstrapping, okay, that lies between these two extremes. That family is TD lambda. Okay, so that's what's going to be the first part of today's lecture. And the second part is getting into a very different topic. By second part, I actually mean parts 3, 4, and 5 in this lecture. Okay, 1 and 2 are the first part, 3, 4, 5 are the second topic. And that topic is what to do when we have a very large number of states. Okay, so that's very common in practice. In fact, it's quite uncommon in practice not to have a very large number of states. So, what do you do about it? That is what we will look at. It's called generalization and function approximation. So, let's get started with multi step returns. Okay, all right. So, again, for illustration, we are going to start by considering the prediction task. Okay, and thereafter, most of these things we do for prediction will generalize to control. So will this. Okay, but let's, for concreteness, look at the prediction problem, which is you're given a fixed policy pi and you're acting according to this policy. You want to estimate what is the value function of this policy, v pi. So let us say at some point of time you have an estimate and then you start going along this episode. Okay, whatever S2 gets a reward of 2 and goes to S3, gets a reward of 1 and goes to S3, etc. Okay, till it terminates. Now with TD0, all right, which we covered last class, we already know that this is the sort of update we will do. Okay, as soon as you reach S3 from S2, you are going to update your estimate of the value of S2. I mean, for simplicity, I have not used time as an explicit suffix over here in these updates. I'm just calling this new estimate and old estimate, etc. Okay, so V new of S2 becomes V old of S2 times 1 minus alpha plus alpha times the target. The target is what you see in red, and with TD0, the target is reward plus gamma times current value of next state. Okay, so 2 plus gamma times V old of S3 in this case. The contrast to this is provided by the Monte Carlo method. So if we are doing first visit Monte Carlo, the update that we will do, right? In fact, the very first update that we will do after seeing this episode, we'll have to wait for the end of the episode, is to set V new of S2 to 1 minus alpha times V new of V old of S2 plus alpha times target. And that target is, in this case, the entire run, right? 2 plus gamma times 1 plus gamma squared times 1 plus gamma cubed times 2 plus gamma to the fourth times 1, okay? Plus, if you want value of terminal state, which we know is 0, right? So it's not written out over here. Okay, so again, for simplicity, by the way, I have not suffixed alpha by time, right? I mean, I think the concept we are going after right now, let's not worry about the learning rate and all that. Let's more look at the targets that we are using for our returns. Okay, eventually we might do this the right way by annealing alpha, etc. Okay, so now the question to you, for you to think about is this. Let me propose a different update from both the TD0 update and the Monte Carlo update. And let us ask, is this a reasonable update to make? Okay, so what is this update? I'm saying let's set V new of S2 to be V old of S2 times 1 minus alpha plus alpha times this target, okay, this target which is in red. So what is this? This is 2 plus gamma times 1 plus gamma squared times V old of S3. So where is this coming from? Okay, with TD0, we took the first reward and then we said gamma times whatever is my current value estimate for S3 over here. Okay, with Monte Carlo, we said we're going to look at more of these returns, go right until the very end, right, and at that point stop. So that's what's going on over here. So what's happening with this proposed update is we are only going 2 steps ahead. Okay, we're not going one step, we are not going all the way, but we're going 2 steps ahead, right? We're saying I'll take 2 from my episode, I'll take this gamma times 1 also from my episode, from my empirical return. But thereafter, I will use my current estimate. Okay, I will start bootstrapping, yes, not after 1 step, but after 2 steps. Okay, the fact that this is also S3 is because the state that you visit, not next, but next and next, right? Like the second state that you visit after S2 is also S3 over here. Okay, so it's from this S3 that we get gamma squared times V old of S3. So can we do this, right? So semantically, it seems to have the same meaning as what we were doing with the earlier ones. The extent to which you're looking ahead before bootstrapping is different, all right? So it turns out that this proposed update is perfectly legitimate to do, okay? And it's called a 2-step return, okay? What you see here in red is not a 1-step return, it's not the Monte Carlo return, it's a 2-step return, okay? And you can imagine also doing 3-step return, 4-step return, etc. in a similar way. So in general, let's formalize what is an n-step return, okay? So let's assume we are going along this trajectory S0, R0, S1, R1, etc. So for n greater than or equal to 1. So in general, let us look at what is an n-step return. For n greater than equal to 1, okay? The n-step return, let us denote it g t to t plus n. Okay, this is the n-step return starting from time step t. Okay, you've reached time step t, you're seeing state st, and the long-term reward starting from there, okay, is what we propose to estimate using gt to t plus n. Okay, so gt to t plus n is reward plus gamma times reward plus gamma squared times reward for n time steps, okay, and at the very end of this you have the value estimate at the end of these n time steps, okay. So gt to t plus n is estimating v pi of st, okay, and it's using this particular update. So take a minute, convince yourself that if we set n equal to 1, okay, what we have over here is what we saw with td0, right? You'll get rt plus gamma times Vt of St plus 1. Okay, when you make n larger and larger, you're going to get more and more of these updates. So we have to be a little bit careful about the episode actually terminating before n steps. Okay, this could happen in an episodic task. So we will go with the convention that if you're trying to estimate gt to t plus n, you're trying to get it, but then your episode ends before t plus n time steps, right? It ends at t plus n prime for n prime less than n. Then what is gt to t plus n? Let's just take it as gt to t plus n prime. Okay, so when you're having a return g like this, which has terminated, right? So you'll only be looking at the empirical rewards. There's really no value at the end of this because you have terminated, and we, by convention, take the value of the terminal state to be 0. Okay, so if we adopt this convention, right, that if the episode ends before n, right, what we have accumulated up to n prime, right, where it ends, we'll define as gt to t plus n. We can sort of conveniently denote as gt infinity the actual Monte Carlo return starting from t. Okay, because if it is an episodic task, then I mean at some point it will terminate, right, and that point will be smaller than infinity. Okay, so this is just by way of definition. So the idea is n step td, okay, sometimes it is called tdn, is a bootstrapping method. It's a learning algorithm that makes an update of this form. It's actually what we saw on the previous slide for n equal to 2, okay. So vt plus n of st, okay, is vt plus n minus 1 of st times 1 minus alpha plus alpha times g t to t plus n. So crucial to note here is that we are waiting n steps, okay, to get our estimate of st. So when we were waiting forever, that was Monte Carlo, essentially n equal to infinity, or n is something large enough to cover the end of the episode. That's like a Monte Carlo update with a n equal to just 1, right? It's basically the td0 update, but crucial to bear in mind is this is t and this is t plus n. The update that you make for st based on gt to t plus n has to wait, right? Why does it have to wait? it has to wait because gt to t plus n has to wait for n steps, right, to get all these empirical rewards and see where you reach after n steps. Okay. The good thing is this is a consistent way of doing the updates. Doesn't matter what n is. If we make updates using n step TD, we will again converge to V pi, just as we know we will with Monte Carlo and with TD 0. So this is like a perfect generalization of both Monte Carlo as well as TD 0, and you can see that the parameter n, right, is actually what is letting us control the amount of bootstrapping over here. Okay, so if we make n larger, it becomes closer and closer to Monte Carlo. If we make n smaller, it becomes closer and closer to full bootstrapping, which is what we call TD0. Okay, but the reason we call it TD0, right, that 0 is not because n equal to 0. Okay, with TD0, n is actually equal to 1. It's called TD0 because it is TD with lambda equal to 0. Okay, so there is something we are going to introduce next. Okay, this is TD lambda, which has a sort of a close relationship with this n step return. Okay, so don't get confused by the 0 and TD0. Don't confuse it with the n over here. It comes from the lambda, okay, which we will see just like a couple of slides down from here. But yeah, we've already gotten some hint that there is a way to control the amount of bootstrapping. Okay, in this case, the parameter n allows us to do exactly that. Okay, now let's take this one step further. Again, I'm making all these proposals to you about possible ways in which we can do our updates. Okay, so now that we know we can do n step updating, let's consider this. Okay, you visited st and then you waited out 3 steps. Okay, at time t plus 3, you want to do an update to S3 to st. So you say its value of st times 1 minus alpha plus alpha times target. Okay, now let's consider a few possible ways in which we can set this target. So can we use gt to t plus 3 as our target? Can we use gt to t plus 3 as the target? By all means. Okay, this is what we did on the previous slide. So it is exactly the 3-step return. So it's a valid way of setting the target. So the answer to this question is yes. Now let's start asking the questions that you've not seen the answers to before. Can we use gt to t plus 1? Okay, so we've gone 3 time steps beyond st. But then we are wondering, well, can I use gt to t plus 1, right? Remember, gt to t plus 1 will be like the 1-step reward plus gamma times the value you had at t plus 1 as your estimate for the state you reach there. Okay, can we use this? Well, it's a little bit outdated information, of course, but we can. Okay, so remember that all of these quantities will eventually converge to V pi. Okay, so it turns out that at intermediate stages, even if they are not fully formed, as long as they are consistent, you can use them. Okay, so you can use gt to t plus 1. Can we use this? Okay, can we use the average of gt to t plus 1 and gt to t plus 2? It's, I mean, not as intuitive to see because we're not even like looking at one return here. We are looking at 2 returns and then we're combining them by taking the average. Is this okay? Turns out this is okay. All right. So we can extend this, right? Instead of averaging 2 things, you can average 3 things. Okay, here we are averaging t plus 1, gt to t plus 2, and gt to t plus 3. And moreover, we are giving them weights. Okay, they're not sort of being equally weighted. So 1/3 comes from gt to t plus 1, half comes from gt to t plus 2, and the remaining, right, 1/6 comes from gt to t plus 3. Can we do this? We can do this. Okay, this is also something that we can do. Now, how about this? Okay, can we do gt to t plus 1 plus gt to t plus 2 plus 3 times gt to t plus 3 divided by 4? Okay, so take a close look at this. One thing you will notice is that this is not really a weighted average. Okay, so if you sum up the coefficients of the 3 g's, right, you have 1/4 here, 1/4 here, and 3/4 here. Now, those things don't sum up to 1. They sum up to something that's more than 1 over here. You cannot do this. Okay, so it's not okay for you to combine them in any way that you choose. It needs to have some discipline. So this is violating the discipline. If the coefficients of the g that you are summing up like this they don't sum up to 1, you can't use it. How about this? Okay, I've carefully picked 3 coefficients that will sum up to 1. Okay, here you have 1/3 of gt to t plus 1 minus 2/3 of gt to t plus 2 plus 4/3 of gt to t plus 3. Okay, you sum them up, you get 1. Can we do this? We can't. Okay, so the reason you can't do something like this is you have a negative coefficient over there. You're not also allowed to have negative coefficients as long as you do any convex combination of the g's that are available to you. Okay, at t plus n or t plus 3 or whatever you're looking at, you can do that. Okay, you can't do it if it's not a convex combination. So what does convex combination mean? It means you have a few quantities that you want to combine, give them weights which sum up to 1, but each weight must be non-negative. Okay, so it doesn't matter if you have some zero weights. So in fact, not including any of the g's here amounts to giving it a weight of 0, right? But you can't give it a negative weight, and nor can you give them weights that sum up to something that is not 1. Okay, so this is a relatively familiar concept. Very often you use convex combinations in various parts of applied mathematics. So this is one of them. Okay, now comes what we are going to do with the n step returns and combining them into what is called the lambda return. Okay, so let us here define lambda return. Okay, so lambda is a number between 0 and 1. Okay, and the lambda return starting at time step t, okay, is a convex combination of all the g's starting from t through the end of the episode. Okay, so you take gt to t plus 1, gt to t plus 2, gt to t plus 3, etc. You're going to give them weights which will sum up to 1. Okay, and all of these weights will be greater than or equal to 0. But what are these weights? These weights are all determined by this single parameter lambda. Okay, and lambda is like an input parameter. Okay, it's been given to you, and the weights themselves are what is defined in this equation over here in the box. Okay, so gt lambda is defined as 1 minus lambda times sum of the gt to t plus n's weighted by lambda to the n minus 1, plus at the very end you have this sort of singleton term sticking out, gt to capital T, that basically just absorbs all the remaining lambda. Okay, this is so that if you add up all the coefficients of the g's, you'll actually get 1. So make sure that that happens. What is capital T? Capital T is basically the time step at which the episode ends. Okay, so yeah, so gt to t plus t is like the Monte Carlo return starting from time step little t. If the episode doesn't end, it doesn't matter. Okay, you can actually take t to be infinity. The lambda return is still something that's like an infinite sum now rather than a finite sum. Okay, so what is to note from this definition? Lambda is an input parameter and it gives different weights to the different g's. Okay, and the weights are sort of falling off geometrically, you can see, right? Or maybe you can say increasing geometrically depending on whether you're looking at lambda or 1 minus 1 over lambda as your ratio. Okay, so the weight is proportional in some sense to lambda to the n. Okay, for gt to t plus n. It's not exactly that, but it's in the order of that. Okay, so let's draw a few inferences about what is going on with gt lambda. So what do we get by setting lambda equal to 0? Okay, so lambda we know goes from 0 to 1, so let's see what happens at the extremes. So at lambda equal to 0, I mean it takes a little bit working out to show gt g0t, right, which is basically g lambda t with lambda equal to 0, will just amount to be gt to t plus 1. Okay, it's the return that is used by td0. The reason I told you have to be a little bit careful doing this is you have to really observe this by taking the limit of lambda going to 0. Either doing that or making peace with the claim that 0 raised to the 0 is 1. Okay, so 0 raised to the 0, sometimes people don't define it properly, but you can define it to be 1. So in this case, the reason you have to use this is, let's just put lambda equal to 0 and see what happens. So each g, right, gt to t plus n is going to get multiplied by lambda to the n minus 1 minus lambda to the n, right? That's the coefficient accompanying it. I'm just moving this 1 minus lambda inside, except of course the last of these terms. So because this is n going from 1 to t minus 1, right? So lambda to the n minus 1 only for the very first of these terms is going to be like lambda to the 0, okay? So if lambda is exactly 0, that's 0 to the 0 multiplying gt to t plus n. But for any lambda greater than 0, right, clearly lambda to the 0 is 1, okay? So you're going to get, as you take the limit of lambda going to 0, this is going to be gt to t plus 1. For every other term, right, we're multiplying lambda to the n minus 1 and minus lambda to the n minus 2, right? And that's going to be basically going to, for every other term, we are multiplying gt to t plus n by lambda to the n minus 1 minus lambda to the n, okay? And if lambda is 0, that's exactly 0, okay? What happens when we set lambda equal to 1? Well, when we set lambda equal to 1, this whole thing goes away, right? So the only term we're going to be looking at is the Monte Carlo return, right? And that's going to be 1 times the Monte Carlo estimate. So now you get the picture, right? As we vary lambda from 0 to 1, we are actually spanning this spectrum from full bootstrapping at lambda equal to 0 to no bootstrapping at lambda equal to 1. Okay, so that's precisely what we were looking for, right? A way to control the amount of bootstrapping. We saw it sometimes back with n itself. It's actually true that the parameter n itself also controls the amount of bootstrapping. Lambda is a lot more convenient to use because it sort of enforces a recursive structure, okay, which doesn't come naturally with n. So you could say that both of them have more or less the same effect, okay, but implementationally, okay, in terms of actually converting this idea into code, lambda is a lot more convenient, right? And in fact gives rise to an algorithm called TD lambda, okay, that's what we'll be looking at next. But take a moment to familiarize yourself with this definition and see that we're going from just using gt to t plus 1 at one extreme to using gt to infinity at the other extreme. Okay, so how do we go about using this lambda return? Okay, that's really what's coming up next. So first thing to observe, as long as we're using lambda greater than 0, right, for any non-zero lambda that we use. So think about it, when you go from st to st plus 1, okay, which states lambda returns does this contribute to? Does this transition contribute to? It will actually contribute to every state that you have visited in the past, okay? Because for that state, right, had you been looking forward from that state which you had visited in the past, right, this is going to be the corresponding g whatever to whatever through t, right, through t plus 1. So a little bit of that has to go back and be used in the update for that state, okay? And you can also see that the longer back you had encountered something, the amount of g that is going to go to it is going to sort of fall off geometrically, okay? Sort of it becomes less and less and less, but it has a non-zero contribution to everything that you have visited in the past. So it turns out that for this particular choice of convex combination, right, because we are doing this geometric some sense discounting of lambda, it's not really discounting in the nature of the discount factor, but the fact that the lambda contribution, the coefficient of the g's is falling off like this, allows us to do a very efficient implementation of this idea, okay, of updating based on the lambda return, okay? So the natural way to first think about it is to ask from every state, right, when I see a new transition somewhere in the future, how much lambda, how much g should I take from that, right? So doing that is called the forward view. What is somewhat more elegant and put into code as sort of implementation is what's called the backward view, okay? So what we do is, as we go along, we keep track of previously visited states and keep track especially of how eligible they are to get some fraction of what has happened in the current transition, okay? So there is something called an eligibility trace that we maintain. It's got an eligibility coefficient, let us say, for each state that you visited in the past. And we keep track of these eligibility values, basically the eligibility trace. And this leads to a very simple sort of intuitive update. Okay. And so precisely implementing this, okay, using eligibility traces to make updates based on the lambda return is what's called the TD lambda algorithm. Okay. So you already have an idea of what we are trying to do. Okay. We are not doing TD0, we're not doing TD1, we're doing TD lambda for intermediate lambda in general. The idea is we have to apportion credit to states we've visited in the past. So let's see how we can do that in a simple and clean way. So I'm going to show you some code on this slide. The central element that we are introducing here, okay, which we've not seen before, is what is called the eligibility trace Z. Okay, so Z associates a quantity called the eligibility with each state that you have visited in the past. Okay, and this implementation, as I said, is called the backward view because from our current state, right, we decide how much should go to previous states. Okay, so I mean, functionally, it's the same as the forward view. Okay, but it's just sort of more convenient to implement it like this, looking back rather than looking forward. Okay, so here's the pseudocode for TD lambda. Let's look at what's happening over here. So as usual, we have a value function which eventually we want to converge to v pi, which we initialize arbitrarily. And then we do the following for each episode. Okay, we start each episode by setting z to 0. Okay, so this is the 0 vector, which is a way of saying you set it to 0 for every state. So the idea of setting it to 0 for every state at the beginning of the episode is, I mean, you've not seen anything yet. What you saw in the previous episode doesn't matter, right? I mean, I shouldn't be updating a state here based on what happened in it in the previous episode. That's been forgotten. I mean, that's not been forgotten, right? I mean, the V will, of course, come from the previous episode, but the Z does not. You start Z afresh each episode. So let's say you're born in state S, and then you go along the episode, you take A, get reward R, and then go to S prime. So delta here, right, is the essentially the portion that you see normally inside the braces, right? When we do these updates, it's reward plus gamma times V of S prime minus V of S. In some sense, that's the material really for the most latest TD0 update. Okay, but now that we have started from S, right, and we have gone from S to S prime, the state that is most eligible, right, that got most recently eligible because of this transition was S, right? I mean, some credit, some part of the G that we have recently come up with should go to S. Of course, it should also go to everything in the past to some extent, but the current state becomes a little bit more eligible. In fact, it becomes eligible by one more than it was before we saw it. And then you do the update. Okay, so the update you do is value of state goes to value of state plus alpha delta times Z of S. Okay, so this is the place where not only are we updating the current state, we are updating all the states that we have visited in the past, provided they are eligible. Okay, so imagine that there's a state that was not eligible. Okay, it has an eligibility value of 0. It's not going to be updated over here. Okay, so because you'll be doing alpha times delta times 0, the value for that will remain S. The eligibility of every state also gets discounted by gamma times lambda. Okay, so this is the right way to do it. Of course, it's being discounted by lambda. This is something that we know, but gamma also needs to be there to maintain the semantics of expected long-term reward. Okay. One thing to note, I'm realizing this as I'm just showing you the code, is think of this state S over here as a local variable for this for loop. Okay, so this state for all S is not the same as the state from which you started. Okay, so if you want, you can call this S bar or something like that, and then use S bar inside of the for loop. But then when we come out of the for loop, right, again we're talking about the S that we had. This is the S from which you started, and then you went to S prime. And so because you've gone one step ahead, right, make S prime your new S. Okay, so just so that you don't get confused, let me repeat, this state is S is different from this state S, okay, and also different from this state S. So just change all the s inside the for loop to something else for clarity. Okay, all right. So we can do this. Okay, this is the backward view of implementing TD lambda. So what's the point of doing this? The point of doing this is the empirical effect of lambda. Okay, so I've drawn a graph for you, just sort of schematically. I've not done this from real data, but here is what typically happens as an effect of lambda. Okay, imagine running TD lambda with lambda from 0 to 1. Okay, so at any point of time t, right, after we've seen t data points or t transitions, how is the value estimate going to be? Okay, so if we compare the value estimate with the actual true value v pi, right, and let's say this norm being plotted here is the infinite norm or squared norm or anything reasonable. Okay, again, this is a rough sort of proof of sketch of a graph. It's not really like something from real data. So what you will usually see is that there is a U-shaped pattern. Okay, the error in your prediction of the actual thing is usually optimized for some intermediate value of lambda. So the reason this happens is that at lambda equal to 1, okay, you're only using Monte Carlo returns, right? And there's going to be a lot of noise in these returns. Okay, so you are going through a stochastic process that is adding some amount of stochasticity at each step, right? So what can happen in t steps or till the end of the episode is very variable. Okay, so there's high variance for high values of lambda. For low values of lambda, the variance is less. Okay, because we're only doing reward plus the current estimate. Okay, of the next state value, but there is bias, right? Because the value estimate for the next state is something that you started off with arbitrarily, right? Maybe you started with zero initialization, maybe you started with something else, but you have introduced some new sort of knowledge into this value table, which might be correct, which might not be correct. Okay, so it's also not good to fully trust the bootstrapped estimate because I mean you are starting with some value. If somehow magically you had the right values to begin with, right? Maybe it'll help to bootstrap, but in general you don't, right? So in general, the right thing to do is to, or rather, the best results you will get with some intermediate value of lambda. Of course, as you see more and more data, right, your value prediction will get better and better and better. So you'll get like a, maybe it'll still remain U-shaped after any finite amount of time, right? But of course, the prediction errors will be less. If you're able to do this forever, right? You take t to infinity, then it doesn't matter what your lambda is. So TD lambda will converge to v pi in the limit of t going to infinity. Okay, that's true for t equal to 0, for lambda equal to 0, for lambda equal to 1, and all the lambdas in between. Okay, yeah. So again, the consequence of lambda, the effect of lambda is to control the amount of bootstrapping. So lower lambda means more bootstrapping, more bias. Higher lambda means more dependence on empirical data and therefore less bias but more variance. Okay, there's actually formal ways of characterizing the bias variance trade-off that lambda manages to account for. Okay, and if you implement this most often after any finite number of steps, right? If you're doing it for 10,000 episodes, 20,000 episodes, usually you'll find maybe lambda equal to 0.9 or 0.95 or something like that. That's giving you the right answer. Usually it will not be either 0 or 1. Okay, so that was TD lambda. Okay, what we have done in the first portion, the first two sections of this week's lecture is look at multi-step returns. We wanted a way of controlling the amount of bootstrapping, so we started with TDN, right, n-step returns, and then we said it's okay to combine them using any convex combination. One particular way of doing it was the lambda return. Lambda has this nice sort of geometric sequence of coefficients, because of which it becomes amenable to a implementation that becomes the TD lambda algorithm. Okay, it gives shape to what is called the backward view of updating using the lambda return. Okay, so what's coming in the subsequent sections of the lecture is a new portion. Okay, it's not directly connected to the lambda return, although towards the end of the lecture we will actually look at TD lambda generalized to what is called linear TD lambda. But before that, let us really sink into the need for generalization and function approximation. So let's take a step back and ask, why are we studying reinforcement learning as a part of this course in the first place, right? I mean, naturally we've been doing a lot of concepts, but eventually, right, it's very applied topic. We want to do it because we want to develop agents that can learn, right, the right thing to do in natural environments. One such, right, which I'm illustrating here is soccer. Okay, so what you're seeing here is a subtask of soccer that is called half field offense. So you can see that it's happening on one half of the soccer field. There's an offense team that's in red and a defense team that's in blue. There are 4 offense players and 5 defense players, one of which is a goalkeeper. You can see what's happening, right? The offense is trying to score into that goal. Defense is trying to prevent it. So you can see that's a pass, and then another pass. Is that going to be a goal? We saw a goal being scored. Okay, so sometimes you will also see episodes on which goals are not being scored. See, each of these players is actually running a separate program. Okay, this is a simulator which treats each player as a process, and periodically the players see what is around them, then they can take actions. Okay, so the defense team here is actually following a, so let me take a minute to pause this and tell you what's going on. So the defense team is following a fixed strategy. Okay, there's 2 players who are just directly going for the ball. Okay, and 2 of them sort of stay back, trying to block the angle between the, or rather block the line between the ball and the goal. And one of them, of course, is the goalkeeper. Now, what is the offense team doing? Okay, the idea of the offense team is to score goals, and that is also the aspect that interests us, right? How can we train the offense team to score goals? For now, what we are doing is the offense player that has the ball, okay, at any point of time, it has to decide which of 5 actions to take. Okay, it can either do a direct shot into the goal, or it can do a dribble. So a dribble is a short kick in the direction of the goal, or it can do a pass to one of its teammates. Okay, it's got 3 teammates, so it can pass to teammate 1, teammate 2, or teammate 3. Okay, see, these are the 5 actions that it has to take as a function of what it sees. Okay, and for now, the offense player with the ball is actually implementing behavior that I have programmed. Okay, so I have written down a strategy using a bunch if then else statements. Okay, if you're close enough to the goal and you see an open angle, shoot. Else, if your teammate is close to you, right, and there's no opposing player in between, then you pass to your teammate, right? Bunch of rules like this. Doesn't matter exactly what they are, but it's a sort of hand-coded policy that the offense players with the ball are following. The ones without the ball are following a fixed strategy. Okay, they try and keep to a formation that looks like a rectangle or a trapezium, but that is fixed. Okay, that's not something that we have any hold on in terms of trying to optimize for now. So what we really are interested in is which of these 5 actions must the player with the ball take. Okay, you can continue watching the video, so you can see that that's a dribble and then a pass, another pass, lots of passes. There, right, they lost the ball. Okay, there was an unsuccessful pass that ended the previous episode. Okay, see that one again, the ball went out. Lots of passing so that they don't lose possession of the ball, but in spite of that, sometimes what do we see, right? Because there is noise in all these actions, by the way. So when you pass to a teammate, there is some noise added to the direction in which the ball will go, right? And that's the reason you can sometimes see the ball going out of bounds. Okay, so the question really is, it seems like a very natural thing to do, to ask the offense player to learn how to play soccer, right? And you can actually formulate this as a reinforcement learning task by giving that player a +1 reward if the ball goes into the goal and 0 otherwise. Okay, this is naturally an episodic task. If you want, you can also give some small intermediate rewards, but strictly speaking, it's not necessary. Can this behavior be learned, right? This association of state to one of these 5 actions so as to maximize expected long-term reward. I mean, this is as obvious or as illustrative as you will get of a sequential decision-making problem where there is a need for learning. So how do we do it? Is there something coming in the way? So now let's get back to our slide deck. All right, so here we go. Back to half-field offense. We are focusing on, remember, the behavior of the player, offense player who has possession of the ball, and that player has to decide as a function of state which of these. Well, I've written three actions here, but there are three different types of pass, right? So dribble, shoot, and three passes. Okay. How do we do this? Okay, well, last class we saw control algorithms, right? We saw Q-learning SARSA, expected SARSA, which actually tell us that you can use a model-free approach to learn behavior. So can we do that? We can do that if we are able to answer this question, right? How many states are there in half-field offense? Okay, because the idea with Q-learning SARSA, expected SARSA that we saw last time involved having an entry for every state action pair, right? And then updating that entry when the transition happened. The only issue here is that we have an infinite number of states, right? So literally every configuration of these players, the ball on the field, right, is going to be a different state, okay? Because what happens from there, right, in general could be different for different states, okay? So not only it's an infinite number of states, it's like uncountably infinite, right? In the sense that literally these are real valued quantities, like the position of each player on the field. And so there's really no hope of putting this whole thing in a table, okay? Because if you put it in a table, you need to have an infinitely large table. You're never going to be able to do anything about it. So what can we do, right? We would still like to do learning on a task like this. That's the whole point of doing reinforcement learning, right? If we are happy with just doing it in small tabular cases, the sort of problems that we can attack is a very, very small subset. You might not be able to extend it to more practical, realistic settings such as this one. Of course, we can do something, and that becomes the basis of what we're going to do in the remainder of this lecture. So the first step is an idea that is specific not only to reinforcement learning, but really all of AI and machine learning. Okay, so this is the idea of using what is called features. Okay, so what do I mean by features? How are we going to apply them over here? So again, in this particular task, it's reasonably fair to say that to define a state, right, you have to specify the positions and velocities of each of the players as well as the ball. Okay, maybe if you want, you can model things like how tired a player is, right? Other aspects which might determine what they're able to do, not able to do. But by and large, right, as a first order sort of as a first order measure of state, right, we can just think of positions and velocities. So I'm using only two offense and two defense in this illustration. The offense is in yellow, the defense is in the goalkeeper is sort of pink or violet maybe, and purple, I think, I'm not sure, this color, whatever it is. And the other defense player is playing red, let us say. Yeah, so if you have like two coordinates for the players as well as the ball, as well as their first derivative, right, with respect to time, you more or less have state. But this is probably not very useful way of representing state. So why is that? So first of all, some aspects of this might not be that important. It might be true, right, that velocities are necessary for defining state, but it might not really matter too much in terms of decision making. Your ability to decide what to do, right, might not depend very crucially on the velocity of players. It might depend to some extent depending on how you're playing, but in a simulation like this, it actually doesn't matter that much. The second aspect is that these coordinates, right, position coordinates like coordinate 1 and coordinate 2, they might not generalize very well. Okay, so what do I mean by that? So what you would ideally like to have is that if two states are similar, right, then the effect of taking an action, right, the same action from both of those two states must also be similar. That's what we would like. Okay, so that if you learn something about one state, you can use it to generalize behavior for a nearby state, right? So we have no way of doing this without generalizing, because if you want to learn something separately for each state, you have to learn an infinite number of separate things, right? That's not going to happen. So we are necessarily constrained to learn something that must have some amount of generalization